Just like with the t-distribution, we now want to be able to use our normal distribution to find normal intervals. And I want to continue to surf through and see what kind of information they gave me, because identification is the key to being able to tell whether I'm using a normal distribution or a t-distribution. So we notice we have a sample of 50 cars, so my n is equal to 50. And the mean times on the dealer's lot is 45. Now that is the mean of those 50 cars, so that is my x bar. Then it ends the sentence and says, assume the population standard deviation. As soon as it tells me this is the population standard deviation, I know that this is sigma, which is my population standard deviation, rather than S, which is for the sample standard deviation, which is also my indication to use a Z interval instead of a T interval. And then we know we want to find the 95% confidence interval for the population mean. So we have a C level of 0.95. So we're going to need a critical value, Z alpha divided by 2, which is equal to the inverse norm. Remember, alpha in this case would be equal to 0.05. Alpha divided by 2 is equal to 0.025. So 0.025, 0, and 1. It's going to give us a 1.96 as our critical value. Then applying this to our formula, we're going to take our x bar, so 54 minus, well, let's find our margin of error first. Our ME, 1.96 times 6 divided by the square root of 50. Now that is going to give me a 1.7. So now to come back to my interval, 54 minus 1.7 and 54 plus 1.7 gives me an interval of 52.3 and 55.7. Just like before, we're very interested in the information or the sentence and interpreting what this has to tell us. So in this case, we are 95% confident that the mean number of time a car is on the dealer's lot is between 52.3 and 55.7 days. Just like we did with proportions, we want to be able to find the minimum sample size necessary that meets the requirements specified by someone doing a study. So in this case, we want to be 99% confident. So my C level is 0.99. Alpha would be 0.01. And we want to be accurate within. And remember that word within is our key, that is my margin of error. So we want to be accurate within 2 feet. And the standard deviation from a previous study is going to indicate that they are treating that like sigma or whatever. So we have almost all the information we need, except we do need a Z alpha, and we always do the Z alpha divided by 2. And in this case, we're looking at about 2.58 if you round. Filling in our formula, we're going to have 2.58 times 4.38, and divided by our 2, and we will not square it until the end. And when we calculate that out, we're going to come out to about 31.97. And remember, it is a sample size, and so we always round up. So we're going to go to 32. Which means the minimum sample size necessary to be accurate within 2 feet is and accurate within 2 feet and 99% confident is 32 measurements. Just like with the proportions and the t-distribution, we can now do this for 2 samples. We want to make sure we identify what we have. So we have an X bar 1 of 88.42 for the room rates of New Orleans, and X bar 2 of 80.61, the room rate in Phoenix. And we have a sample size for each that is 50. So N1 and N2 equal 50. And their prospective standard deviations. And notice again, they told you specifically this is the population standard deviation. So population standard deviation is 5.62. And sigma 2 is 4.83. And we want to be 95% confident. If we remember from above, our Z alpha divided by 2 is equal to 1.96. Now the margin of error formula is slightly larger, but nonetheless doable. So 1.96 times the square root, I'm going to take the given standard deviation, 5.62, and square it, and divide by 50. Then we're going to take our 4.83, square it, and divide by 50. Once we calculate that out, we're going to see around 2.05, depending on where you're rounding for this margin of error. And then we still need a point estimate. And that's the 2 X bars subtracted from one another. So 88.42 minus 80.61. It's going to leave us with 7.81. So my interval is 7.81 minus the margin of error of 2.05. 7.81 plus that margin of error, 2.05. Our final interval is going to be 5.76 to 9.86. And we can say we are 95% confident that the mean difference in room rates between New Orleans and Phoenix is between $5.76 and $9.86. Notice that this interval is totally positive. There's no negative numbers, which means that even though we don't know for sure, we know that 95% of the time, the room rates in New Orleans are going to be larger than the room rate, higher than those in Phoenix, because our interval is always positive, and we took the average hotel room rate for New Orleans and subtracted that of Phoenix and got a positive number. So 95% of the time, the room rates in New Orleans are going to be higher than those in Phoenix, which is what we would expect because a lot more people are going to travel to New Orleans than probably Phoenix, and so they're going to be more popular and the rooms will cost more there. A researcher reports that the average salary of assistant professors is more than $42,000. A sample of 30 assistant professors has a mean salary of $43,260. At alpha equals 0.05, test the claim that assistant professors earn more than $42,000 per year. The standard deviation of the population is 5,230. So we want to identify what we're given. And since the claim is in here that we're more than 42,000, that's an indication that mu is equal to 42,000. We have a sample that is 30. We have a x bar, which is our sample mean of 43,260. And we have a standard deviation for the population. Notice again, they did not put it in the same sentence as about our sample. It has its own sentence. And then they told me specifically population standard deviation. Now we need our null and our alternative. So in this case, we have that mu is equal to 42,000. And then they are saying that it is more than that. So mu should be greater than 42,000. And that is also where my claim is. Now we can use the formulas above and kind of plug it in and say that our test statistic is equal to 43,260 minus 42,000 over 5,230, which has to be divided by the square root of 30, which is our sample size. And when we simplify that out, we're going to get a z-value of 1.32. Now again, if I'm doing this by hand instead of using the assistance of technology, I'm going to use critical values to help me. Now this is a one-tailed test, so we have all of our alpha in that one upper tail. And it is in the upper tail since it's a greater than test. And we know from up above, or we can do an inverse normal, that our critical values are going to be 1.645. And if we are in this tail, we will reject. Noticing that we actually have a 1.32. We have fallen in the non-rejection region. So we are going to fail to reject, which means there is insufficient evidence to support the claim. And again, I'm using the word support because the claim is in the alternative, so we're not rejecting it, we're just not supporting it. And the claim that assistant professors mean salary is more than 42,000. We're going to go back to our room rate problem, but this time we are going to test the hypothesis on it. And we want to know, can we conclude that there's a significant difference in the room rates? Well, let's just to collect our information once again. We have x bar 1 equals 88.42 and x bar 2 equals 80.61. N1 is 50 and N2 is also 50. Sigma 1 is 5.62 and sigma 2 is 4.83. And of course, alpha is our 0.05. Now we are testing for a difference, and just like when we did it for t-distributions, we're looking at the mean of the first one equal to the mean of the second, or the mean of the first, in this case, not equal to the mean of the second, because we are looking for that difference. We'll find our test statistic. Before we do that, since I am doing this by hand, we want to use a z alpha. And this time it is divided by 2, because anytime it is a two-tailed test, we are splitting that alpha up among the two tails. So we'll have two critical values. And if we recall, this one was 1.96. So we're going to have a minus 1.96, positive 1.96, and we're going to look to see what is in these tails. Now our test statistic is going to have to include all the data. And we've got 88.42 minus 80.61. And again, since our base assumption is that mu1 is equal to mu2, if I subtracted mu2 to the other side, and I'm assuming they're equal, and I subtract them, that portion of the formula is going to equal 0. And that is always the case. Mu1 minus mu2 should always be 0 in that formula. And then, of course, we have to fill in our standard deviation formula, which is 5.62 squared divided by 50 plus the 4.83 squared divided by 50. Simplifying all of that out should lead us to 7.45. Now this is not even on our picture. It'd be way over there. So since it's not even appearing in the picture, we are going to definitely reject the null and say that there is sufficient evidence to support the claim that the average room rate between the two cities is different. Now, does this align with what we said about this back when we made the confidence interval? If we go back and remember, when we built this interval, we had all positive numbers. And in order to reject a hypothesis looking at the interval, we want to know, is the number in our hypothesis test in the interval or is it not? Well, in this case, the number that is in our hypothesis test would be mu1 minus mu2, which we have to assume is equal to 0. Since 0 is not in this interval, we would also reject. If the number in your hypotheses is outside your interval, you are going to reject the null hypothesis. If it was inside the interval, we would fail to reject. So in this particular case, we do get that our interval and our hypothesis test are telling us the same thing, which should always be the case, especially in t-distribution and z-distribution. There are rare cases in proportion where that is not the case, but most of the time they will agree, and if they don't, we want to go back and make sure we didn't have some kind of calculation error and try to make sure that they do match up.